Alright guys, we're going to try and use a new piece of technology today for 8.4, rational expressions. I'm hopeful that this thing works out, so keep your fingers crossed. A rational expression, as it says here at the top, is the quotient, and that should make us think division, of two polynomials. So when we're talking polynomials, think like we did just last section here when we said a polynomial is p of x over q of x. That's what we're using here for our rational functions. It is in simplest form when the numerator and denominator are polynomials with no common factors. Okay, so simplest form, let's talk about a few examples of what that might look like. You might have something like 1 over x. That is simplest form. It cannot be reduced at all. Or maybe you have something like this, x minus 3 over x minus 5. That also cannot be reduced at all. That is in simplest form. You could also have something a little bit longer, maybe say like x squared minus 4x plus 5 over x plus 7. So even though there's a lot of terms going on in that thing, that is also in simplest form. It cannot be reduced. Now, one of the things that we're going to look at a lot is trying to factor to make things eliminate. We did that a lot in 8.3 when we started looking at discontinuities. Let's look at some examples of expressions that are not reduced. And this is what we're going to spend some time doing here today. When stuff is not reduced, sometimes it's fairly obvious, like say this one here, x to the second over x to the fifth, right? That's going to simplify down because you have x's on top that can cancel with the x's on bottom. This is going to become 1 over x to the third. Let's look at another one. We'll call that example 1. This I'll call example 2. Let's say you've got 3x minus 6 and you're dividing that by x minus 2. Well, the thing we're going to want to do here is look to factor. And in this function, we can factor on top. So I'm going to pull out a 3 and make it 3 times x minus 2. And we're going to divide that whole thing by the bottom, which is also x minus 2. Now, hopefully you look at this and you start to see something match up. You know, hopefully with discontinuities, that got us in the mindset of thinking, all right, maybe stuff on top can cancel with stuff on bottom. And that's what we want to have happen here. The x minus 2 on top will cancel with the x minus 2 on bottom. So, to get that thing down to simplest form, it's going to be just 3. Make sense so far? Okay. Let's look at another one that we can try and simplify down. I'm going to call this one number 3. Let's say we've got x squared minus x minus 6 all over x squared plus 4x minus 21. So both of these are quadratic trinomials. Hopefully it jumps out to you that we can factor these. I can factor the top and factor the bottom. When I factor the top, this becomes x minus 3 times x plus 2. When I factor the bottom, that should become x plus 7 times x minus 3. Now notice that I'm running parentheses around everything, even when I don't necessarily need it, like I did back here up here in example 2. The reason I'm choosing to do that now is because it helps us see these as individual terms. And individual terms are easy to identify as things that will cancel. So obviously x minus 3 and x minus 3 are going to go away here, leaving us with x plus 2 over x plus 7. Okay. Let me do another one here. Say this one's number 4. Let's write it as x squared plus 4x over x squared plus x minus 12. Now, when we factor, one thing that jumps out to me with the top here is GCF. Let's not forget about that. We haven't used that in a little while, but there's clearly a greatest common factor in the top part here, and that's an x. So when I pull the GCF out, that leaves me with x times x plus 4 on top. And then the bottom splits down into x plus 4 times x minus 3. So again, we can see what cancels here, right? The x plus 4 on top and the x plus 4 on bottom are going to go away, leaving us with just x over x minus 3. So again, that's just how we reduce. Factoring is a friend here. It's going to be helpful. Now, like it says here at the bottom, like before, we have to be aware of domain restrictions. So when we're dealing with fractions, remember the key thing that affects our domain is we don't want the denominator to equal 0. And I said that before in 8.3, think denominator. So denominator cannot equal 0. So using the examples from above, I'm going to go back up and grab number 1, we reduced down to 1 over x cubed. So I'm using the same things from above, 1 over x cubed. What's going to cause us problems here in the denominator? Well, that would be if our values of x were 0. Like if I plug in 0 for x, it's going to give me 1 over 0, and that's an issue. So our domain here is all real numbers except 0. Okay. Number 2 from above. We ended with, what was it? We ended with just 3, but I'm actually going to back up, and I'm going to use this piece that was 3 times x minus 2 over x minus 2. So right before we canceled out the x minus 2's, that's what I'm going to use. When we talk about domain restrictions, you always must account for everything, even if it cancels. So I'm going to make a note on that here, that we must account for everything before it cancels. Think about like discontinuities. We talked about how there's removable discontinuities, and how I showed you guys on, I think some of you guys on a graph, how when the table came up, there's an undefined output that went with that removable discontinuity input. And that's how this plays out here. Like, even though this is going to cancel, if you try and plug 2 into this function, it's going to cause us problems. Our domain here is all real numbers not equal to 2. Remember, removable discontinuities create that hole in the graph, which makes it discontinuous. We talked about that a bunch the other day. All right, number 3. That one from above should have been x minus 3 times x plus 2 on top. All of that was over x plus 7 times x minus 3 on bottom. So even though the x minus 3's are going to cancel here, we still have to account for them in our domain. So we have all real numbers here except for negative 7 coming from the first factor and 3 coming from the second factor. And the last one over here, number 4. So we've got x times x plus 4 divided by x plus 4 times x minus 3. Like we just did above, we would cancel out the x plus 4's, but in terms of the domain, we still have to count for everything. So not equal to negative 4 and 3. Okay. So far, so good? All right, let's go to the next page. We've got a few examples to do there. The next page says multiplying rational expressions. So now we're taking two expressions and we are multiplying. It sounds actually a lot harder than it really is. I'm going to give us 2 steps to follow here. These 2 steps are going to be crucial. If we can follow these, it's going to make life very easy for us. Number 1, factor when possible. And that's going to appear in a variety of ways, which we'll talk about in a second, but we always want to look to factor. If we can do that, that'll cancel things out. It'll make life easy for us. And then, like I just said, number 2, we want to look for things to cancel. It's really just a two-step process. Factor when possible, and then look for things to cancel. So I got a lot of blank space here. I'm going to write some more examples in for us. Number 1, let's write in the expression x plus 2 over x minus 3, and then we're going to multiply that rational function times x squared minus 9 over x squared minus 4x minus 12. Okay, so you look at this and it looks pretty overwhelming probably, right? There's tons of stuff going on, right? All kinds of x's, all kinds of signs, parentheses everywhere. What the heck is going on? All we have to do is break it down one piece at a time and try and go back to our first 2 steps. Number 1, factor when possible, and then we're going to look for things to cancel. So on the top left piece here, the x plus 2, does that need to factor? No, but it's by itself. We're in good shape. Let's look at the one below that, the x minus 3. Does that need to factor? No, that can't factor at all. How about over to the top right now? We have x squared minus 9. Yeah, that's a difference of squares. And that's, let me finish writing this. That's a situation that pops up from time to time. And so we got to remember how to factor that. Difference of squares factor is x plus a, or a plus b, and a minus b, thinking back to when we first did that. So this is going to be x plus 3, x minus 3. And then on bottom, x squared minus 4x minus 12. Yeah, that should factor down as well too. That should factor down to x minus 6, x plus 2. Okay, so now here's the other thing, guys. Even though we are multiplying these two things, we can really just combine them into one. When you multiply fractions, you multiply straight across. So we can really just think of combining this whole thing into one big expression. And the reason I say that is because it doesn't really matter if we have like the x minus 3 down here and the x minus 3 on the right side. Even though one was on the left, one was on the right, it's still top and bottom. When we combine them together, you're going to cancel those out. So that gets rid of the x minus 3's in both cases. Anything else that can cancel? You might look through this and say, oh yeah, x plus 2 and x plus 2. Great. So that leaves us with x plus 3 over x minus 6. And if we're talking domain, which we need to remember that, we can use all real numbers here except whatever was on bottom. Now remember, we got to go back to the big expression before we canceled when we talk about domain. So that would be 3, 6, and negative 2. That's all we got to do. That's it. Factor when possible, look for things to cancel. I know we called it multiplying, but we're actually not really even multiplying stuff. It's just called that because you're actually multiplying the expressions, but the way we approach it is we just set it up, you combine things, you factor things, then you cancel things. That makes life pretty easy for us.